Hello everybody, welcome to this new specialist video. I'm here today with Dr. Erik-Jan van Kampen. He is one of our assistant professors in the section of control and simulation. Welcome Erik-Jan, thank you for being here.
Thank you.
And for giving us some advice on stability and control basically. If we start let's say in the beginning of the DSE, we have of course our user requirements, and that is typically at system level that the system has to do something, and from that the students, they will derive their functional flow diagram. What kind of elements related to stability and control will pop up in that functional flow diagram?
Yeah. First of all, thank you for inviting me, Erwin. I'm happy to give some explanations about the control and stability aspects of the design process for the DSE. And usually the first thing that you have to look at when you start your design is to think about what your vehicle has to be able to do. And this comes directly from the functional analysis. So there are certain requirements set by your supervisor or the project leader, and from that you derive certain functionalities. And you can think of it as what should the vehicle be able to do, and it could be an aircraft like this. So does it need to be able to roll and pitch and yaw and follow a certain trajectory? You can also think about satellites. Do you want to do attitude control? Do you want to do orbit control? And we have also a lot of assignments with UAVs or drones, like a quadrotor. And then you have to think about what kinds of degrees of freedom do you need to fulfill your mission. So I would say that's the first thing to look at. What are the degrees of freedom of your vehicle, and what are the requirements for all the degrees of freedom?
So can you give any examples of these degrees of freedom? Because this is kind of an abstract term, of course.
Yes, of course. So I'm holding this aircraft, so let's look at an aircraft. You could have requirements on roll maneuverability. So you need to be able to turn the aircraft in a roll with a certain rate, which can be derived from either requirements, airworthiness requirements, or it could be related to a certain mission. If your aircraft needs to perform a certain mission, and for that it needs to be able to, for example, track something, then from that you can derive your requirements for accelerations, or for attitudes, or for velocities.
Okay, clear. That's clear. But I can imagine that so if I understand correctly, any motion around an axis, either a translation or a rotation, that's basically a degree of freedom. And if you do a maneuver, you want, of course, that this maneuver is stable. But also, if you don't do a maneuver, you want to be stable as well, right, with your system. So how does the stability and controllability link to these degrees of freedom?
Yes, that's of course very important. So once you have identified what degrees of freedom you need, then you have to think about stability and maneuverability. So we want to be able to maneuver in certain degrees of freedom, and you want to be stable in certain degrees of freedom. And for that you need to think about if the aircraft has to be stable, or a satellite, or a UAV, are you going to provide this stability yourself with active stability implementation, or can you design the vehicle in such a way that it's what we call passively stable? And for example, if you look at an aircraft like this, they're designed usually in such a way that they're also passively stable. So if you get a disturbance, if you get a disturbance in angle of attack and pitch angle, due to the shape of the aircraft, it will correct this disturbance. So it's passively stable in some directions. Other vehicles, they might not be passively stable. If you have a quadrotor, that's normally not stable, or any type of helicopter. So if it's not stable passively, then you need to actively make it stable, and that's done by means of implementing a control system. So then we can actively control some actuators or engines in order to provide stability.
Okay. Well, if we, let's say, dive into this passive stability, I can imagine that, you need to have, of course, a model of your system first. So I would call these the equation of motion, of course. But yeah, you mentioned the example of the angle of attack perturbation. So you have this damped out oscillation basically, which is driven by the aerodynamics. So there is a lot of, I would say, interaction between the different fields and your motion, your equation of motion. So can you elaborate a little bit on the modeling aspects of your system?
Yes, yes. So as soon as you have found out what kind of maneuverability and controllability you need, it's time to start modeling. So you need to make a mathematical model of the vehicle that you're trying to design, because it can help you in, well, first of all, determining what the control system should look like, but it can also help you with the other parts of the design. And usually the best thing is to have a first order design of your equations of motion. And for your equations of motion, Newton's equations, you need to know the forces, the moments, and you need something to know something about the masses or inertias. And that's where you need to talk to all the team members in your group, for example, the structures people and the aerodynamics people, because they need to give you information on what are the forces and moments, and what are the masses and inertias. And even if it's a preliminary estimate, you can use that to build a mathematical model of your vehicle, such that you know if certain forces and moments act on the aircraft. If you know the inertia, then you know what kind of acceleration you will end up with.
Okay, clear. Yeah, you mentioned the several aspects, the aerodynamics, the structures. I can imagine propulsion systems should be also play an important role. How far do you go? I mean, we know that we are doing a conceptual design, of course. So we start very simple and we have our trade-off and then we go into the detailed design. But even the detailed design is still conceptual. So do you go for the full-blown nonlinear equation of motion, or is it possible to linearize them or to approximate your equations?
Yeah. Well, that's a very good question, and it's also something that students are often struggling with in the DSE. And I always say that the most important thing is that your all the aspects of your design, so not just the control system, but all the aspects, they have to be designed in a similar level of detail. So it makes absolutely no sense, for example, if you talk about the quadrotor, to model it with a sixth order model for dynamic inflow of the rotors. With all kinds of fancy nonlinear modeling methods, because the rest of your design still has uncertainties on it, 10%, sometimes 25%. So then it doesn't, it won't give you anything extra if you have a super detailed simulation model. And so always start with first order principles, and check with the other aspects of your design that you're not making one aspect super detailed compared to the others.
Okay. Yeah, let's move on now to controllability. So basically, how would you approach the design of a control system? I can imagine that, in our bachelor program, we teach certain things. No doubt that we have introduced the concept of flow diagrams, block diagrams. So how would you go about into setting up the first design of your control system?
Yeah, so as a control engineer, I would say start with drawing some block diagrams, as you also know.
Yes.
But of course, you need to think about what you've been taught in the second year course on control theory. And there you've looked at, let's say, classical control theory, so for linear systems. So that's also why it makes sense to start off with a linear model of your aircraft. So you make a linear model, and then you can use the tools that you have learned in the control theory course to design a linear controller for such a system. For example, a PID controller. And if you remember the things that were taught in the course, then you know there are some analytical approaches to tune the gains in your controllers. And also there are numerical methods. You can also tune them numerically. But I would say that it's important when you think about the control system design that you think about which inputs does your controller need to generate. So are we talking about control surfaces, are we talking about engines, or about rotor blades that are tilting? and what kind of desired response do they need to achieve. So you have an input, for example, the elevator that you want to use to control the pitch angle. And those inputs and outputs you can link to each other in a controller. You can use a block diagram for that. You can think about uncoupling the different modes, the different degrees of freedom, and then you can make a nice block diagram of the structure of the controller.
Okay, but I can imagine that you in principle you want to have a single input that gives you a single output of your system. So what we know as to be decoupled systems. So I can imagine that you may want to have a controller for the longitudinal motion and one for the lateral motion. So in how far can you decouple the system of equations?
Well, that depends on your system, of course, the vehicle that you're trying to control. For fixed-wing aircraft like this, it's a reasonable assumption to decouple the longitudinal from the lateral equation of motion. Especially if you don't do very crazy things like very high bank angle turns. For other vehicles, it may be very difficult or maybe even impossible to decouple it. If you look at helicopters, they have some very strongly coupled dynamics. So then it will be difficult to make a controller that only works for pitch and a separate controller for roll and yaw, because they will interact a lot. So I would say it depends on the vehicle, but yeah, try it first to make a decoupled controller. And if you see that there are strong couplings, then you need to do something smarter. For example, with helicopters, although the dynamics are very complicated, we do have some knowledge about it. We know what will be the side effect of an input on one channel, what will be the side effect in the other channel. So if we know about it, we can already sort of beforehand compensate for it. And when we give a certain input on one channel, we know it will result in a side effect that we don't want, so we can already compensate for that.
So that's typically feed-forward control, I guess,
yes,
right?
That's the feed-forward part. Yeah.
Okay, that is clear. So yeah, now let's assume that we have a certain controller structure. Let's go with the PID controller, and we are going to tune the gains. So I can imagine that we have to check the performance of the system now with the requirements that we have set up right from the beginning, right?
Yes, and that's it's very important that you have clear requirements. Otherwise, you can design your control system, but you don't know when it is good enough.
Yes.
So look back at your requirements, and for example, it could be related to the stability aspects of your vehicle. And then requirements can be given in terms of damping ratio of a certain eigenmode, or the natural frequency of a certain eigenmode. And then in your PED tuning, you can tune the gains in such a way that you satisfy those requirements. Sometimes you can do it analytically if your model is simple enough. If it's not simple enough because you still have some nonlinearities or some strong coupling, then you can do it numerically and also with a trial and error process, but not just in a dumb way, but in a smart way. Because you do know generally what is the effect of increasing a proportional gain or a differential gain or an integral gain, and with that you can tune your control system.
I can imagine that it is important that you really look in detail into your requirements, because what we always say, better is the enemy of good. So don't make your requirements too strict. I can imagine that if you can do with a 10 degree per second rate, don't go for 20 degrees per second, because it will complicate matters, right?
Exactly, yeah. And if you sort of over-optimize in one criteria, usually that means that you're giving away something in another criteria. Yeah. So it's usually not a single requirement that you're optimizing, but it's a whole bunch of requirements. And then you will see, if you do the optimization correctly, that you end up somewhere, let's say, on an edge of all these requirements. And so not somewhere in the middle, because then you're overcompensating.
I guess that Murphy has said that there's no such thing as a free lunch, right?
Exactly.
Yes. Okay, great. So we're reaching now actually the implementation inside our system, our satellite, our aircraft, our quadrotor, or any other UAV that we might have. Are there any, let's say, hardware considerations that we have to take into account?
Yes, of course. And then this is let's say you've made this initial design, you have a simulation model based on, for example, a linear model. So you have some results, you have tuned some of your gains, but what you have modeled is not what the vehicle is going to be like in real life. So in real life, when you have actuators or engines, they're not perfect. They're not linear, they have delays. Your flight control computer that you use to implement your control law is also not infinitely fast. So there's also delays there. All of these things will have nonlinear effects on the performance of your closed loop system. So although it goes a bit too far to design your controller to deal with these nonlinearities already from the start of the design, you can do an analysis to see what is the effect of these kind of, let's say, perturbations or uncertainties after you have designed your controller. And you can use that to make your controller more robust.
Okay, but I can also imagine that if you would take all these aspects into account and you go for an actual flight qualified system, there's many steps after the DSE that have to be taken into account, and which also leads to a cost aspect. So is there anything that you can say about the cost involved in actually fully developing such a system?
Yes, so at the DSE, even when you finish the DSE, you still have what I would say a preliminary design. And we know we call it detailed design, but for industrial standards, it's still quite preliminary. And then there's a whole process of verification that has to be performed. So every line of code has to be verified, all the functionalities have to be verified. And this comes at quite a large cost. So I don't know exact numbers, maybe you know something more about the cost per line of code, but it's a very expensive process. And not only in software, but also the hardware itself has to be flight tested. So you need to show to the authorities that your system will do what you specify it will do. Yeah. And you do that by flight test.
Yeah, and in the end, the groups, they have to come up with a reasonable costing, because the cost target that has been given is actually for the final design. So yeah, all those aspects which you have to do after the preliminary design, you have to take into account into the costing. So you have to have some insight in the flight testing. It's typically $500, $600, $700 or something like that per line of code, including the verification, including the testing, including the documentation. So you can imagine that if you have a very, very complex system with a couple of million lines of code, that it is a tremendously high cost post. So and you really don't want to, let's say, jeopardize the project by underestimating that part. Okay, I think we have more or less reached the end of the interview. Is there anything that you may want to add?
Yeah, maybe one more thing. When you are modeling your vehicle, it's also nice, although not strictly necessary, to visualize what your vehicle is doing. So for example, if you are working in MATLAB Simulink, but it could be other programs, and you can connect your outputs of your vehicle, your states, to for example, a 3D model that can move around in a virtual world. And seeing your vehicle moving around in a 3D world, seeing the effect of your inputs, of your controller, can really help you in understanding what's going on, much better than just looking at a line in a graph. So I would say try to do that as well.
Yeah, I think that is an excellent advice, because it is very hard indeed to judge what this abstract curve mean. Okay, so with this let's say pearl of wisdom, we are going to end this interview. So Erik-Jan, thank you once more for being here and helping us out with answering some questions. So thank you.
You're welcome.